So we have a type II PLL which has a 3-state phase detector which gives you the up and down signals, and these control current sources that flow into and out of the capacitor. Okay, and this goes to the VCO. So this arrangement that puts a fixed amount of current into the capacitor, this is known as the charge pump. Okay. Basically, in one period, it puts a certain amount of charge into the loop filter. That's why it's called a charge pump. This is the output from the divider. So, firstly, ideally, if A and B are coincident, then up and down will both be an infinitesimally small blip. Okay. So both of these, the 3-state phase detector consists of 2 flip-flops which are reset if the outputs are simultaneously high. Okay. Now, in the ideal case, we assume that the AND gate reacts instantaneously and the flip-flops react instantaneously to the reset signal. Okay, so what happens if there is AND gate and reset delay? Okay, so let's say this is no reset delay. We can combine the reset delay of the flip-flop and the delay of the AND gate, right? That is the time taken between A and B going simultaneously high, up and down going simultaneously high to them going back low. Okay? So what happens in this case? What will be up and down? So let's say it is rise time is not the issue, but there is some delay. Okay, so then, so it will be like this. No, if there is no rise time, there is no triangle. It's just this is the amount of time it takes for the reset to happen. Okay. Isn't it? Okay, what is the output now? The output in this case was the difference between up and down, so it was 0, and in this case also it is 0. So what is the issue? Is it clear? If we are analyzing only the 3-state phase detector, let's say we have some delay through the delay for the reset path. That is the delay for through the AND gate and also through the reset pin of the flip-flop to its output. So that is the total reset delay. So if you do have a non-zero reset delay, what happens is up and down will both be rectangular pulses whose duration is equal to the reset delay. Okay. The output is still 0. The output is the difference between up and down. Or is it? Okay. So what happens if the currents are not equal? Okay. So what will you get as the input to the loop filter? So let's say this is I1 and I2, or ICP plus delta I and ICP minus delta I, 2 delta I. Where will the loop stabilize? Will it stabilize to a 0 phase difference between the input and the divider? Huh? No, what is lot? No, that's okay. What is the operating point of the, see, if
Even if there is no phase difference, you will have, you can't determine the output.
But the feedback
There will be some range of values.
Why can you not determine the output?
the feedback does not know that there is mismatch. So we should be able to estimate.
Why not? Why does the feedback not know? Does it have a definite operating point or not? Does the circuit have a definite operating point? It has. So you're saying only I am incapable of analyzing it. Okay. When does the loop reach steady state? So let's say this is now we have established two things. In the ideal case, of course, there is no reference feed through because the phase difference between the reference and the divider output is 0. Okay. In that case, individually the up and down signals are 0, which means that no current is forced into the charge pump. Sorry, no current is output from the charge pump into the loop filter. Okay. So what is the meaning of steady state? Output of the loop filter? 0. Why 0? What should be the same? So there should not be a long-term drift up or down in the control voltage. That is the meaning of steady state. It doesn't have to be 0, it can be different from 0 also, right? If the output frequency is not equal to the pre-running frequency, it will in fact be non-zero. Okay. So first, the ideal case. In that case, up and down are individually 0. So the currents, both these switches are off. This is off and this is off. So the current going into the loop filter is 0. So the loop filter will hold its voltage. So that is steady state. Okay. Now what happens if there is reset delay through the in the phase detector, but there is no mismatch? If there is no reset delay and no mismatch, the phase of the divider equals the phase of the reference, and up and down are 0. Okay. Now let's say there is a reset delay, but no mismatch. Then still the phase is 0. So what happens is both up and down are rectangular pulses of equal duration. So for a while both switches are on. So there is a current ICP flowing like this. Okay. So no current flows through the loop filter and the loop filter voltage is still constant. So that is the steady state. Okay. Up and down are not necessarily 0, but they are high for the same duration. So the current is still 0. Okay. If I call this the current output of the phase detector, that is 0. Let's say we have reset delay and mismatch. What happens? How much is the phase difference? How do you figure that out? Loop transfer function at what frequency? Why does the, how do you get this? Okay. Yeah. So what I was asking for was the operating point. So it's not really related to the transfer function of the VCO, right? So again, the steady state is when there is no long-term drift of the control voltage. That means that the average value of this IPD, lowercase IPD, must be 0. Okay. Now, let's say the up current is ICP plus delta I and the down current is ICP minus delta I, right? So what will be the steady state phase difference between A and B? 2 delta I by. So essentially we have A and B, there will be some phase shift. That phase shift depends on which one, whether the up or down is higher. Okay. Now let's see, if up current is higher and the down current is lower, what we need is for the DC value to be 0, the up should have a narrower width and down should have a wider. Okay. Both get reset simultaneously. So the up should look like this and down should look like this. So will B be leading A or lagging A? B will be leading A in this example, right? Okay. So this is A, this is B. Now it is consistent. Meaning this amplitude is ICP plus delta I. This is ICP minus delta I. Okay. So up minus down is ICP minus delta I for this period. Okay. And for the width of the reset pulse, so this is the reset delay, right? That's the amount of time it takes for the reset to happen. And for that period it is, sorry, this is negative, right? So before the reset it is minus ICP minus delta I, and after the reset it is what? 2 delta I. Okay. So 2 delta I times the reset delay should be equal to ICP minus delta I times the phase difference, or basically phase difference by 2 pi times the time period. Okay. So from this we can calculate the phase difference. And if delta I is very small, we can just say okay. So the mismatch between the two is delta I, 2 delta I. Okay. I have taken plus delta I and minus delta I. So it's the difference current divided by ICP. That is that's the relative phase delay between the two. Okay. So as the mismatch increases, the phase difference increases. And what is the input to the loop filter? It is this waveform. This is periodically repeated. In every cycle you get this type of waveform which has an average value of 0, but it has components at FREF and its harmonics, right? It's a periodic signal at FREF. So that will give you the reference feedthrough. Okay. No, the A and B are the D inputs. A and B are the inputs to the phase detector. Okay. Yeah, that's correct. The D inputs of the flip flops and a phase detector are 1. Huh? No, I didn't understand. ICP plus delta I should be what? Yeah. Okay. What I have plotted there is really is controlled by up and this is controlled by down. So, what I have plotted is the logic value of up times the value of this current. Okay. So, essentially the total current IPD that flows is up value. Let's say up is represented by 1 and 0. When it's on, it's 1. When it's off, it is 0. So, up times the top current source and minus down times the bottom current source. Okay. Is that correct? That is the current that is flowing out into the loop filter. Okay. So, what I have plotted is really this much, just for getting a more intuitive feeling. I mean, yeah, of course, up is a logic signal, so it has an amplitude of 1. I mean, it doesn't make sense to talk about amplitude. The state is either 1 or 0. Okay. What I have plotted is the state of the up signal times the current that it is passing. Yeah. So this is down times I bottom, this is up times I top, this is down times I bottom. So this whole thing is, it's not up minus down, it's up times I top minus down times I bottom. So that's why it is negative and positive. Okay. So it has to be both negative and positive for its average to be 0. Right. So what you get into the loop filter in case of non-zero reset delay and charge pump current mismatch is pulses like this with an average value of 0 going into the loop filter. The period is FREF and the amplitude depends on the amount of mismatch and the reset path delay. Okay. Is this okay? So again you can calculate this is the steady state. Once you calculate the steady state, this current flows into the loop filter. So you can calculate the control voltage of the VCO, and from that you can calculate the amount of frequency modulation, which gives you the reference feed through at the output of the VCO. Okay. Loop filter input waveform looks something like this. Graphically, it will look like this. This is for the case where the top current is more than the bottom current, and this is ICP minus delta I, negative of that, and this is plus 2 delta I, and the area under the negative part has to be equal to the area under the positive part, and this is the reference period Tref. Okay, and the width of the positive part is T reset. The width of the part which has 2 delta I is T reset. Okay, the width of the other part can be calculated. That is 2 delta I by ICP times Tref, T reset by Tref. Okay. So, and you can calculate the Fourier components of this and find out the reference feed through. Okay. So, this is a periodic signal going into the loop filter. So, at the output of the loop filter, that is the control voltage will also have periodic components at Tref, and that in turn will give you a frequency modulation of the VCO. Okay. So, how much will this reference feed through be compared to that in the type 1 PLL? It will be of the same magnitude. Let's say the bandwidth and all that is the same. Okay. Let's say the loop filter, we can't say the same loop filter because the loop filter there is no loop filter in that case. So, what do you guess? In this case also there is reference feed through, but is this reference feed through comparable to that with the type 1 PLL, or is it less, is it more? It will be much smaller. Why? Firstly, the width is small and the amplitude is small. The amplitude is small and the duration is small, right? Typically, if you have a certain phase difference in a type 1 PLL, the error signal will have a shape like this. Okay. So, error signal is the zero average signal that goes into the loop filter, and the amplitude of this, the peak to peak amplitude of this is ICP, and then it persists for the entire period. And if the phase shift is more, then it becomes even larger. Okay. Whereas here it is related to the mismatch. If the mismatch becomes smaller, you get much better results. Okay. The phase shift itself is related to mismatch, and the amplitude of this, the area of this is related to the mismatch. So, the reference feed through, there will be reference feed through, it is not 0, but it is much smaller than in the type 1 PLL. Okay. And of course, we can put additional poles to further filter it if necessary. So, this is because the area under the pulses is roughly proportional to mismatch times the reset delay. So, by reducing the reset delay and reducing the mismatch, you can reduce the reference feed through. And in any case, it will be, you can expect it to be orders of magnitude, at least an order of magnitude better than in the type 1 PLL. Okay. Type 1 PLL had other problems as well, that of lock range, but even besides that, the reference feed through in this case is much better. Okay. This is even if you didn't have additional poles, but you can also put additional poles to further attenuate the feed through. Mismatch in the divider, meaning? No, but what is it? Like mismatch between what and what? No, but that's not, that won't happen, right? It's a frequency counter, you can count n cycles. It will count n edges, maybe the n edges are not uniform. That means that that is what the jitter of the VCO is, that's the phase noise of the VCO. Okay. So, the VCO edges may not be uniform because of imperfections in the VCO, but the counter you can expect it to count n edges. Okay. Now, in reality the counter will also have its own noise. So, let us say the first edge comes at time 0 and the next edge of at the output of the divider will not come at the nth edge. It will come slightly away from that, I mean before or after it because of noise, but that noise is usually very small, okay, compared to the corresponding edge noise of the VCO. Typical value of delta I. So, delta I by ICP can certainly make this better than 10%. So, this is the relative mismatch on the current sources, right, rather 2 delta I by ICP. You can match 2 current sources to better than that. I mean, at low frequencies, this matching can be 1% or something of that sort, right. It's not very difficult to do that. Now, there are other things also that come into picture. So far we have assumed that we have the up switch and the down switch and they operate identically and so on. But now you have a current source pumping current out of a node and another one pulling current into a node. So one side will be made of NMOS transistors, the other side will be made of PMOS transistors, and they won't switch in an identical way. Okay. So in addition to this type of, if you turn one switch on, you will get some current. If you turn another switch on, you will get a slightly different current. That is the steady state mismatch. Okay. But in addition to that, let's say you turn one switch on for some time, you will get a current pulse like this. From the other one, you may get something like this. Okay, there will be transient mismatch as well. So because of all that, there will be extra mismatch compared to the steady state mismatch. But even then, you can get it to be, let's say, around 10% or so. Okay. So that's the only thing that's there in the design of the charge pump, to make the 2 current sources match and switch fast. What will be the? Oh, the current source, firstly, yeah, it should give you an accurate current, and secondly, this control voltage has to move over a certain range, right? Now, this, I have schematically put the switch on top of the current source. It can be at the top, it can be at the bottom, that depends on the implementation. But whatever it is, over this entire voltage range, the current source should behave like a current source. A real current source always has a voltage limitation, right? If you use an NMOS transistor as a current source, it won't work if the output voltage is very small. Okay? So, you should design it so that you don't constrain the range. Okay? So, if the VCO needs to be operated over a certain range, you have to have the current source also operate like a current source over that range. Otherwise, the mismatch will become too much. Okay? Let's say at the bottom of this range, this has gone into triode region. It's supposed to give you a current ICP, but it gives you something less. This is now a systematic mismatch. Whereas this is giving you ICP because it is comfortably in the saturation region. So, there will be a big mismatch and big reference feed through. So, as you tune the synthesizer or the VCO, the voltage here will change and that will also change the characteristics, but the specification would be that you minimize it to the extent possible. Okay. Of course, you can't operate these current sources with zero voltage, so you have to leave some room at the bottom and some room at the top for the current sources. Yeah. Yeah. If the reference frequency? Yeah. Yeah. No, in this case there is no effect, right? Because it's sensitive only to the edges. So it's sensitive, let's say, to the positive edges of the two. So it doesn't matter. That's why we came to this kind of phase detector also. So the duty cycle output of this doesn't matter. Any other questions on this? Is it clear how you get reference feed through in a type 2 PLL and how to analyze it, how to determine the magnitude? So once you have the value of the mismatch and the current source value, so in steady state case you can do this easily. Now the transient mismatch you have to evaluate it with simulation clearly, right? So that depends on the implementation and so on. So, but once you have a charge pump design, you can simulate it, see what the mismatch is, and then from that also see if the reference output, reference feed through is consistent with what you see. Okay. How do you connect what? Oh, you have to make the current sources good enough, this and this, and make sure that they switch cleanly. That is, the switching time is identical as much as possible. Okay, but beyond that you can't do anything. I mean, there are different topologies, like some advantages to having the current source at the bottom, some to having it at the top. So you have to evaluate it for your case and see which works. Yeah, we don't have again too much time to go into the circuit design details. In the assignment, I have given you one particular charge pump topology. That is this. I think you are quite familiar with this circuit now. So you want a switch current source. So again, one way to do it was using a differential pair which controls the current. Okay, it steers the current either to the left side or the right side. So let's say the left side is connected to some fixed voltage, half the supply, and the right side is what goes to the loop filter. We have a single-ended loop filter, single-ended control voltage for the VCO. So we can only take one side of this. Okay, so this is the loop filter. Similarly, you have a PMOS counterpart on top. Okay, now this is controlled by the up signal. So okay, and I don't imply that these will go from 0 to VDD. There may not be CMOS logic levels. You have to see what is the right logic level to switch this differential pair. Okay. If the, yeah, I mean that would be better actually, but generally it is hard to arrange that. Okay. So in that case you can not connect this to the fixed voltage, but have a differential loop filter. I mean differential loop filter meaning you just take it and replicate the loop filter, that's all. Okay. Huh? So now if you do have a VCO with a differential control, this is what you do. Okay. So at high frequencies typically it tends to have you tend to make a simple VCO with a single-ended control. When you use these electronically variable capacitors like the junction diode varactors or MOS accumulation capacitor, it is convenient to make a single-ended control. Okay. You can't make it differential very easily. The control voltage you can't make it differential. But if you do have it, then you make an arrangement like this and drive it with a differential charge pump. Okay. What is reverse? The up and up. Up bar and down bar are the same. Yeah, that's not correct, I think, because when up is high, so this should, yeah, if it is reverse, I have to correct it. So when up is high, it has to push current into the loop filter, and when down is high, it has to pull current out of the loop filter. So I have assumed that you are comfortable enough with differential pairs, and I just gave that problem. Okay. Any other questions on this? Do you require any? Yeah. Yeah, one thing is, see, it's ideally the control voltage of the control port of the VCO doesn't draw any current and there is no leakage anywhere. So let's say there is a leakage current. Okay. So what happens? This voltage will drift. So what happens in that case? Huh? The feedback will take care of it, right? So if this voltage drifts, the frequency of the VCO will slowly change. So that means that the phase shift between the reference and the divider will also slowly change. So that will not let this charge pump output be zero. That will give you a non-zero charge pump output which will restore the voltage. Okay. Right now, no. Right now we are only talking about periodic signals. So this will only, whatever we have discussed so far, will only work for periodic inputs when you want to generate a periodic clock output. Okay. So the next thing we will be discussing is how to make it work for data. Will this work for data? The same phase detector? Yeah, so this is a 3-state phase detector. We saw that it will tend to go to one state when edges of A are more frequent than edges of B. Now if you have clock and data, the number of edges in the clock is definitely much more than the number of edges in data. Okay, so it will always go to one side. So this will not work for random data. How would you make it work for random data? What is an essential feature of a phase detector that works for data? So data, I mean, the only thing is it's not periodic and you can't guarantee that there is an edge every cycle, right? That's the distinguishing characteristic as far as phase detector design is concerned. So how would you make a phase detector work for data? No, that is the entire clock and data recovery circuit. Now I am only talking about, see, now we know how to detect phase difference between two periodic signals, right? Our 3-state phase detector will do that very well. It has a range of plus minus 2 pi and it has the output average is proportional to the phase difference between the periodic inputs. Now, I want to detect the phase difference between a clock and certain data, because I can use the same principle, right? How did I get to this circuit? I wanted to align the frequency of the output with the frequency of the input, or some multiple of it. So now I want to do the same thing with the clock, but now my input is not a periodic signal but data. I want to generate a periodic output whose frequency is exactly same as that of the data. So I can use the same principle, that I can detect the phase difference between clock and data, but how do I do that?
The counter after a certain accumulation increases this.
How will that help? Is the question clear? So basically I want to, exactly the same block will work with a data input if I find the right phase detector, right? I have to, the rest of the circuit is the same, at least you can intuitively feel that it is the same, because all that is doing is, in response to a phase difference, it's correcting the VCO. So now I need a block that detects the phase difference between data which doesn't have guaranteed edges every cycle and clock which is periodic. What were you saying?
You can have a counter after and depending upon how much output we get.
So let's say now this is data and this is clock, okay? And you are saying you count. How will this help?
We can at least tolerate a certain number of clock emissions.
But I mean, this is a losing game, right? Because maybe the counter is 1000, but it will only go in one direction, isn't it? Okay, first thing is, right now the circuit we have is this. It works on the rising edge of the clock and rising edge of the data. Is that what you want? That is okay. That's a detail, right? Let's say we have a 50% duty cycle clock and do that or something. Let's not worry about that part now. Okay. That is the key to having a phase detector work for data. The phase detector should work only when there is a data transition. When there is no data transition, it should not be doing anything. Okay? So that has to happen. Right? When there is no data transition, there is no meaning of phase detection. I mean, it's not some practical difficulty. Philosophically, you can't say. If you have all ones, like what is the period of data? You can't say. Right? It can be like data at 1 gigabits per second, 2 gigabits per second, anything. If it's all one, you just cannot say. It's only from the transitions that you can say data is of some period. And also, when there is no transition, there is no point in detecting the phase, trying to detect the phase. It's only when there is a transition that you have to detect the phase. So somehow you have to come up with a circuit that will work only during transitions and is inhibited outside of it. Okay? And also it has to work when data transition is going up as well as going down. There is no distinction between the two, right? So and it is inhibited when there are no transitions. Okay? So you have to have this feature. So we kind of switched gears because someone asked a question about data, but are there any more questions on the PLL? One thing we have not done so far is to evaluate the transfer functions from each point to the output. That's a relatively simple thing to do, but we'll do it afterwards. Okay. So since we have started on this, let's go to phase detection for data. How would we do this? Only when data changes do we want something, right? One more flip-flop where? So I have one flip-flop. What do I do? Where is the clock? Where is the data? Data is the clock. Okay, that is one way of doing it. And input is still 1. And where is the clock? Now? Normal PFD after this. No, first of all, this itself is, once you have an edge, it will give you 1 without reset. Yeah. And also, I mean, you need the clock, right? So, by the way, let's say the data period is this much, okay? This is the period of the data. Then the clock will be like this, okay? So, in each period it has a rising and a falling transition. And for now, let's assume 50% duty cycle for convenience, okay? So, let's say the clock is like this. In this case, I have shown it as aligned. Okay. So, let me make it slightly misaligned. So, the phase difference is basically the difference between this edge and this, or this edge and this. We always look at the same edge of the clock, right? The rising edge of the clock. And here, no edge, we can't make a measurement. And here we have an edge, and we have an edge, okay? So essentially it should work on these phase differences. And during this period when there is no transition, nothing should happen, okay? So how do we get this? Falling edge of? No, but what is the input to the flip-flop? We have to find the phase difference between clock and data, right? So where is the clock, where is the data, where are the flip-flops? What is the input to the flip-flop? 1. So we have data, and this is 1, this is also 1, 0. Okay, what happens now? Where is the clock? Okay.
whenever there is a edge comes in the data, we just pass the output. Like you can put some detector in data, and whenever there is a pulse output of the data, we put some detector kind of.
So you are saying you will make a phase detector. Firstly, that will work on both edges of data, or maybe the rising edge of the data, and then you will inhibit the output later after you do the edge detection, right? Yeah, that's also possible. But okay, all these things. I mean, there are many phase detectors, right? Even the three-state phase detector is used widely because it's a simple one that is very practical. But there are lots of others. Similarly, here also there are many solutions. But what I was trying to get at is something that is used fairly widely. But of course, you can make a lot of variants of that, and also you can come up with something newly. One key idea is because you need it only when data is changing, you can feed data to the clock of some flip-flop and try to do that. So that is one way. Okay. What I will try to derive is something else that is a widely used linear phase detector. Okay. So now we know that this much is the phase shift. Okay. Now let me ask you this: can you get a data waveform exactly the same data as this, but whose edges are shifted to this point, whose edges are shifted here? Is that possible? Clock. Okay. So if I do this, so let's say this is clock and this is data. My output will be what? It will be this. Okay? Is this okay? So it will be exactly the same data, but the edges will be shifted to our shifted clock. Now can I find the phase difference between these two? How do you do that? And? Can you do it simpler? Use an XOR gate. If I use an XOR gate, I will get pulses like this, right? So that's so I first align the data to the clock, and then I use the XOR gate between the original data and the retimed data. So that now I know that the retimed data is aligned with the clock. Okay. So that's basically all I need. Right? So if I XOR it, I get pulses whose width is proportional to the phase difference. I have. If the clock has jitter. No. What is? There are two separate things. What is jitter and what is duty cycle? No, I mean the data edges will also have jitter, right? That is true. I mean that is true with anything. I mean, so if the clock has jitter, the output of the flip-flop will have the same jitter, right? If it's an ideal flip-flop, when the clock transition occurs, the output transition occurs. So if the clock edge is jittery, the output edge also will be jittery. Yeah, so you will get some error in the phase measurement. You will get a noise in the phase measurement. But you are still measuring. I mean, your clock is jittery. So you are measuring the phase difference between the data and the clock correctly, right? But the clock is jittery. If the jitter is too much, you have to do something to the clock source. Okay, it's not, this is not a problem of phase detection, right? It's just that your clock has jitter and your measurement includes the jitter. Okay? Meaning, I mean, you are trying to measure the phase difference between data and clock, and the clock happens to have jitter, so you will measure the jitter also. Now, if the jitter is too much for your purpose, you will have to improve the clock. Okay?
So we know again have the same problem as the first XOR statement.
Why? Duty cycle of what? No, this is happening only at the, anyway, I think we have the next class starting soon, but think about it, okay? So,
Similar to that of the XOR data,
output is similar to that of XOR phase detector, okay?
so we'll have the same problem as what we had to the representation.
No, first of all, we never discussed the XOR phase detector. The main problem with the XOR phase detector was that it was sensitive to duty cycle. In this case, there is no duty cycle sensitivity, right? Because everything is happening only at the rising edge of the clock. Isn't it? What are the other problems with the XOR gate?
The reference feedthrough will be high.
Reference feedthrough will be high. Lock range is limited, but the lock range limitation we got rid of by going to a type 2 PLL. So we can do the same thing here. Okay?
Still there is a larger AC waveform riding on the average beat.
Why? No, anyway, let's continue this tomorrow. Okay? That's not the case.